This is part 2 of Unit 7, Lesson 2, Slope Fields. And this part is going to be made up of 2 examples and then a list of helpful hints to how to tell one slope field from another. So let's start with a matching example. It's possible that you could be given a multiple choice question. Of course, it's not going to have 8 slope fields. It'll have 4, and you have to pick which one goes with the given differential equation, or vice versa. You'll be given a slope field in the multiple choice, and you'll have to pick which differential equation goes with that slope field. So it's important that you can look at things and decide how to match them up. So that's what we're going to do in this example. So what I like to do is look for things like, where is the derivative going to equal 0? Because then I know that I can find horizontal lines very quickly by looking at the slope fields, because those tangent lines will be horizontal because they'll have 0 slopes. So like for number 1, when I look at that, I see that if x equals -2, dy dx equals 0. The other thing I want to take note here is, because this is a square root, x has to be greater than or equal to -2. So I should look for a graph where that part of the grid has no slope lines at all. And if you notice in letter D, what I have is that's the only graph here where there is a vertical section where I have a cutoff x value right here, and all of this is blank because I can't be below that value. So even without looking where the zeros are, although they would be along this line, like you can see right here, those are almost horizontal, that this slope field represents the first differential equation. So number 1 is D, so that one's out. The next one is I want to look at is that for number 2, since it's x times e to the -x, and also the fact that there's no y in the differential equation, as I move up and down a slope field, all those slopes should be parallel. All those little lines should be parallel because it's not dependent on y, just x. So it doesn't matter which y you're at. All the x values, one particular x value as you move through any y value will give you the same slope. So I'm going to look for that. But I also want to notice here that if x equals 0, dy dx equals 0. Another thing to look at is that because e to the -0.2x squared is always going to be positive, that when x is greater than 0, the dy dx is going to be positive, and when x is less than 0, my differential will be negative. So I'm looking at something like that. So what I see is that if you look at letter A, all of the lines for negative x's here have negative slope lines, and all of the positive x's have positive slope lines. And you'll notice as you move up and down the coordinate plane, those lines are parallel, and on top of that, they are flat at x equals 0, which is the y-axis. So number 2 is A. Okay, so for number 3, what I want to remember is that if I just look at where x equals 0, I'm just looking at sine x. So along the y-axis, I should be looking at something near the y-axis that looks like a cosine graph. Because remember, sine is the derivative of negative cosine. So I'm looking for a flipped cosine graph near the origin, and then it's going to be shifted left or right by a value of x. So when I look at that, and again, I want to take note to the fact that if x is positive, if I have a positive x, whoops, that's kind of messy, it's hard to see. So when x is positive, this is going to be positive, and when x is negative, my differential equation will be negative. Okay, so when I look through these, what I see is this happens at G. I can kind of see the pattern of a cosine graph in the center here. And then what you'll notice is on the negative side, all of these slope lines are negative, and on the positive side, all of these are positive. So number three is G. Okay, number 4, I think when you just have either cosine or sine, it's pretty easy. You're just looking for the opposite. So remember, cosine is the derivative of sine. Do any of these slope fields look like a sine graph? And the answer is, look at letter H. Now letter F kind of does, but you have like these vertical parts here along F. So that's not really a complete slope, a complete sine graph. But if you look at H, that is exactly a sine curve. You can see it goes through 0 at the origin, and it goes up and down like that. So this is a sine curve in all those slope fields. So that makes number 4 H. So now I didn't mark the other ones off. So A's gone. What other ones are gone? D's gone. Let's see, G and H. So that leaves us with E, F, and B. Now, right away with E, I'm going to look at that one because what I can see here is that Y has to be greater than 0. So if I look at any of these graphs, which of these not graphs, but differential equations, which of them can I not have a Y equal to or less than 0? And it turns out to be the very next one we're doing for 2 reasons. First of all, we have in the denominator Y cannot equal 0, but in the numerator we have ln of Y. So remember, our natural log curve looks like this, so Y has to be greater than 0. So E has to be number 5. Okay, number 6, what we're looking at is the fact that this is going to be positive everywhere. So every slope of all these little tangent lines are going to be positive. That's the first thing. And the next thing is that, well, actually, that's enough. For if you look at the ones we have left, I guess I don't have to go into any more detail. If you look at the ones that we have left, B, C, and F, the only one that has all positive tangent lines is C. Not only that, I kind of like do the derivative or the antiderivative in my head. That's going to be a cubic graph, and you can actually see the cubic graphs right here in letter C. So don't forget about that. You can use the idea of, if you know what the antiderivative is going to look like of each of these, you can use that to determine what the slope field is going to look like as well. Okay, so the first thing you want to see on the next one is that you're going to have horizontal tangent lines when x equals 0 and y equals 0. So you should have horizontal lines along the x-axis and the y-axis. That should be an indication right away. Now you can't see them in B here for that. The other thing you want to notice is as you move along the lines y equal x or y equal negative x, you're going to have parallel lines as well because of this relationship of negative x, y here. So this is going to be letter B, just from knowing this case right here, because you have horizontal tangent lines here and horizontal tangent lines there. And then so that leaves us, the last one is cosine of x plus y is going to be letter F. And what you want to notice here is if you just let x equal 0, you get cosine of y. And if you look along the y-axis, you can see that you do have a sine graph right at where x is 0, right along here. So you have that as well. Not to mention that where they are opposites of each other, you can see that along these lines, you have that you're going to get that value of -1 for that. So that's going to be F. So that's how you go through trying to determine which slope field goes with which differential equation. Okay, the last example for this section, example 5, a differential equation, a point, and a slope field are given. Use the slope field to sketch a particular solution through the point. Then use integration to find the particular solution of the differential equation. Okay, so I already put the point on there. The point given is 0, 1. And then one thing to notice before we sketch this, there's something odd happening here at -2, and you can see that from the differential equation. That 1 over x plus 2 is not going to go away when we integrate this, and so we want to notice that there is a vertical tangent line at -2. And you can see that from the slope field as well, is that before, from the left side, if you're taking the limit, you have very steep slopes that are negative, so it's heading towards negative infinity. And from the right-hand side, you have very steep positive slopes. So we do have something happening there. So the curve, the graph is going to curve around that point. So let me just clean this up, re-put in my vertical asymptote here, and then I can draw my equation. So what's going to happen with my equation is it's going to, see, let's do the positive part. It's going to skim along these, wait, I don't want to use red. It's going to skim along these slope lines here, like that. And then it's going to come down and go along here like that. So it's going to look something like that. Okay, so let's verify that we have the right solution based on this initial condition and this differential equation. So let me rewrite this. So this says dy equals dx over x plus 2. Now I'm going to integrate each side, the left side with respect to y, and the right side with respect to x. And, oops, I wrote dx over dx because I was saying that. So this should be x plus 2. And if you want to use u substitution here, you can. You want to think of this as 1 over u du, because you let u equal x plus 2. So du will just be dx. So we're going to get y plus c1 on the left, and then we're going to get the natural log of x plus 2 plus c2. Putting my c's together, so I get y equals the natural log of x plus 2 plus c. And that's exactly what the slope field showed. We have a natural log graph that has been shifted 2 units to the left, and that's exactly where our vertical tangent line is, and that's the exact shape that we get from following these slope lines in there. So now what we want to do is we want to make sure that we have our particular C. So we're going to solve for C now. And excuse me, how we do that is we use the given point. So what we're going to do is we're going to say that y is 1 equals the natural log of 2, because you have 0 plus 2, and then we have our plus C. So C is going to be 1 minus the natural log of 2 is C. Now it's kind of awkward looking, but it is a constant, so our final function will look like this: the natural log of x plus 2 plus 1 minus the natural log of 2. And you don't really need the absolute values anymore. So that's that, the answer to that one. Okay, and then finally, what is a nice list of things to think about or strategies that you look for when you're matching slope fields? First thing to think about is when you look at dy, look at dy dx, does it have an x? As part of, and just an x. So what you want to notice is if it's just dependent on x, the slopes are going to change as you move from left to right only, not up and down. So you just have to move your eyes left to right. So in other words, if you look up and down, all those lines, in a particular x value should be parallel. So the slopes change left to right. And I'm going to put only anyway. Okay, what if it only has a y? Then the opposite is going to be true. So now, if you look left to right, all the slopes will be parallel. That way, all those slope lines will be parallel because it's not dependent on the x, just the y. But if you move up and down, the slopes are going to change. So the slopes are going to change up and down only. Okay, next. What if it has both x and y? Then what's going to happen is you're going to have the slopes are going to change in both directions. So it makes it a little more challenging. And then you want to think about when is the slope positive or when is it negative. So what conditions make dy dx positive or dy dx negative? Because that'll help you determine where to look. So if you see that pattern in certain quadrants or in certain sections of the graph that dy dx is, the slope field is all showing positive slope lines, then you can help you look back at the differential equation and decide, well, why does that happen and where does that happen? And then, of course, another very important one is, and this is usually the one that I start with, which is where is dy dx equal to 0 or undefined? Because it makes nice sections of the graph easy to point out. Because then you're looking for horizontal tangent lines in the case of the differential equal 0, and blank spaces if the dy dx is undefined. So go through and look again at the matching ones and see if you can understand that a little better. We're going to talk about this in class tomorrow, and I will take any questions then.